So thanks very much for inviting me here, and it's a great occasion. I'm very glad to be here. So people say we don't choose our relatives, and we almost don't choose our colleagues in our academic fields. So if there's someone quite as perfect as Avram in your academic field, you're very fortunate, and I consider myself very fortunate. And I hope he'll continue his contributions to his level of perfection to the field for a long time, which he will because of his being forever young. Okay, so happy birthday. Okay, so I'm going to discuss a topic which is well lined up with what everyone else has been talking about, I think, but from a slightly different angle. So let's start with the notion of trust. So if you switch on your computer tomorrow, you can trust that in your next interaction, the LLM will produce nice English paragraphs. There's no mystery for people in this room because LLMs are based on well-understood principles of machine learning. But I claim that if you wake up tomorrow morning and you ask an LLM to give you advice on some important life thing, then you won't trust it. Okay, it's different. So what's the difference? And to my mind, there's no great mystery. LLMs are not based on any principled reasoning, and I think here the problem is fundamental. Well, it's at several levels. So one is obviously that no principled reasoning. Principled reasoning isn't programmed into LLMs. A more fundamental reason is that we don't even agree as humans on what reasoning should be in this context. So it's a pretty fundamental problem. Anyway, so that's what I'm going to explore. And so I've been talking about this thing for about 25 years, I think. So I suppose there's a conventional wisdom that it's computationally unaffordable to add principled reasoning to LLMs. It's expensive to add principled reasoning to learning systems. And so I don't like the word hallucination, but maybe scatterbrained is the right how I think of an LLM. That it's kind of, it doesn't quite take the word seriously, doesn't quite identify the right thing. So, okay, so LLMs are saying scatterbrained, and so I do actually have a new idea here, a new suggestion, which I'll try to describe. And very roughly what's going on is that this approach to reasoning has been usually correctly dismissed as being computationally quite expensive. But now LLMs have focused our mind. We know exactly what needs to be done. It's a very definite focus of attention. So what can possibly we do to improve the reasoning capability of inside the LLM to something which we think is somewhat more principled. So that's where I'm going. So very quickly, well, we're coming from computational learning theory. Okay, so we like to identify phenomena, which I think we like to identify phenomena. That's our job. And if you can make artificial systems which exemplify the phenomena, then that's great. But we're also interested in human behavior, so we get inspired by human behavior. So in the 80s, computationally scalable learning from examples is what this field dealt with. But I think the problem of our time in this era is really adding reasoning to learn knowledge. And I think this has been the problem of our time for a very long time. But okay. So the probably approximate correct model already referred to is the idea, main idea is that under very general conditions, the prediction error will go down dramatically with the computational effort you make in doing it. So as I say, this was the center of attention in a certain field from the 1980s onwards. I naturally believed in it, but thought that there was an important next step to take, which is to add reasoning. I think the reasons why this wasn't much interest was, on the one hand, at the beginning, people didn't believe in this. People didn't believe in learning. So why should you add reasoning to something which you don't believe in? Okay, that's logical. But now, of course, what's happened is that people believe in this too much. Okay, people think that this curve will solve all our problems, and we won't have to. Okay. So in fact, okay, so certainly one finding in AI has been that if you've got more and more data, then you may as well do just some general purpose learning from examples, and everything else is redundant. So arguing that reasoning is something special, it needs special attention, is a subtle argument. So, but I think it's I've always believed in it. Okay, so very briefly, my path has been that been talking about this for 30 years, I think. So robust logic is a system which I published in the year 2000. And the basic idea there is that you take seriously the fact that the knowledge, you've learned knowledge, the knowledge is uncertain, it's got a certain semantics, but it's the semantics of this back learning. And somehow you have to be able to reason with it, and you have to abandon reasoning methods which really make sense in this task of semantics. Okay, and that's kind of, that's basically still what I'm trying to implement. So as a rephrasing of it, I decided about knowledge infusion. The idea is that what we need to do is to build systems which have a lot of learned knowledge inside them, but then you want a principled method of using the learned knowledge carried out computationally feasibly to do something useful. So this seems pretty obvious because this is now what language models, we expect language models to do exactly this now, but of course language models historically evolved from a different perspective. This wasn't the aim was as a chatbot. So this idea of reasoning in this AI system is quite subtle, so I clarify some of my thoughts in this book on educability, which appeared a couple of years ago. So very roughly, the notion there is that there isn't one. The fact that we can't agree on what reasoning is some reflection on the fact that there is no one notion of reasoning. There's no robust notion of reasoning, but what we can hope to do is to provide some layer of support for reasoning. So the idea being that as humans, much of our civilization was built on discoveries, and some of the things we discovered were best thought of as new methods of reasoning. So arithmetic is a new method of reasoning, very powerful. Probability theory, new method of reasoning, very powerful. But we had some support in our minds by which we could learn the rules. If someone taught us rules of inference in this method of reasoning, or we learned them by example, then we could run with it, and wow, it became much, much more powerful. So somehow this is the philosophy, I think, which I'm trying to pursue. So of course, recently, suddenly, there was great interest in reasoning and learning systems, because that's exactly what LLMs purport to do. And so basically what's new is that what I have is some proposed implementation of a core case of this robust logic, which before looked like being computationally infeasible, but it looks that you can implement it in a reasonable way in current LLM technology under some heuristic assumptions. Okay, so now very briefly, forgot when I started.
20 more minutes.
20 more minutes, okay. 20 more, okay. Okay, so I'll tell you what robust logic is. So the idea is that we want to learn rules from data, and we are going to learn rules from data, and then we also want to be able to chain together these rules and make predictions. Okay, so if you go, and so if your data is natural language, and someone tells you that Bob insults Joe and Sue likes Joe, and then Sue takes revenge on Bob, well, the idea is you read many of these sentences from novels, you see them in movies, and then you generalize, you figure out what this notion of revenge is. And you want machines to be able to learn these notions and also to reason on them. So in a robust logic rule, basically, you will learn something like this. It looks vaguely like logic, but isn't. It just adopts the notation. So on the right-hand side, there is right-hand side. So you're trying to predict something. You're trying to predict whether two objects, one is going to take revenge on the other, and then you have a condition which kind of guarantees that this happens. And you want to say for any two objects, and then the condition may depend on the existence of further. There's some quantification, and the most important first thing to notice is that this is an equivalence. So in machine learning, we learn to recognize, elephants, true elephants, false elephants. It's not an implication because these are the things machine learning systems learn. You worry about errors in both directions, okay? So anyway, so you can guess roughly what that means so far. And then the idea is simply that if you've learned a rule like this, and if you read some new text, and notion of revenge isn't in there, you want to be able to apply the rule and deduce that indeed, you want to deduce that make a deduction about whether revenge is going to take place. Now the rules are slightly more complicated. So for example, typically, you also have always in the rules, because typically if you want to predict some condition, usually there's several alternative conditions, subconditions, which may guarantee it. Okay, so the general rule maybe does bad to, but insults is one example of does bad to. So you're going to learn these general rules and then apply them in particular cases. And then the idea is that there's a way of making sense of these, which say that these chaining together will be sound in a probabilistic sense, analogous to where soundness is used in logic, which roughly guarantees that when you chain together two rules and each of them is supported by data, it's maybe for you to have 90% faith in them, then when you draw a conclusion, you should have faith maybe to 80%. Okay, so what is chaining? Okay, so now I should just explain more carefully what I'm doing. So the idea is that you, within this robust logic system, there's a notion of a mind's eye. It's like a working memory, maybe in a brain, where there's some tokens, and each token you can assign some attributes. So maybe I look at two tokens, and I assign the attributes. I know that I'm talking about these three people, Sue, Joe, and Bob. And then in my mind's eye, I can also insert relationships between them. So I may deduce that one likes the other, and the third person likes the one, insults the one who the first person likes. And this what goes on in my mind's eye. And then I invoke a rule which I've learned, maybe a rule which says that if I insult someone, I'm doing something bad to that person. And then I invoke another rule which says that then the first person will take revenge on the third person. Okay, so this is a way of mapping learned rules into a more traditional world of logic. Okay. So as I said, we're going to learn these rules, and we're going to apply them in this mind's eye. So this isn't totally theoretical. So a while ago we did some experiment. As it happened, this was a natural language experiment. This was in 2008. We had a small language model, a laptop size, so a small database from a Wall Street Journal, and we were trying to predict missing words. Like not next token prediction missing words, and we were doing this for just the frequently occurring words because it was a small data set. And the problem we're trying to answer is that, is the one kind of I started with, is just for predicting the next word or the missing word, is using some standard machine learning method, can it be improved by adding some logical implication. Okay, so you could throw your standard machine learning thing at this. And then in addition, you throw in a bit more of this robust logic and see whether you're doing better in prediction. So now doing this experiment, how you do it is quite subtle, because how do you measure whether it's a fair contest, how much effort you're putting into various things. But we did, this was done with Loisios Michael, but we did find that with some effort, so here, these 246 words we were predicting, so we erase these 246 words, we're trying to predict which ones occurred in these spaces, and these are ordered from left to right, and the ones on the right are the ones which our method did best for, and they should look at this difference between E and D. So on the right-hand side, there were some words where by using some reasoning, we could really predict their presence much more accurately than others. There were some others where the noise introduced by the method, in fact, flipped things slightly. So but there's some indication that one can do that this robust logic is kind of.
Was the logic learned as well? This robust logic was learned?
Well, the rules were learned. Yeah. So we learned rules on the same data. So this was Wall Street Journal. So we learned rules about profit and that kind of stuff. And yeah. So what rules are allowed in robust logic? So this is more the theoretical end. So okay, so these are what the rules look like. So we call the left-hand side what's inside these quantifiers, and not the right-hand side. Okay, this is called the left-hand side. We could try to consider special classes of left-hand sides which are within certain schemas. So for example, this example belongs to this schema where you've got two predicates and they share one variable x and not the other two, okay? And then it's existentially quantified. Okay, well, so maybe okay. Okay, so sorry, so this one isn't represented in any of these, but anyway, it's the third one, okay? So anyway, what I'm saying is that you can abstract away the schemas by just regarding, instead of looking at particular predicates, you look at the generic ones. Okay, but also most useful are where you only use existential quantifications here. So what this means is that okay, here. So all this notation discusses what's in your mind's eye. So there exists means there exists in your mind's eye some object with some properties. There exists isn't some reference to the outside world. And also for all isn't a reference to the outside world. It's just a reference to what's in your mind's eye. So it's all very extremely concrete. Okay. So as far as the more general theory, we can deal with left-hand side, which are just belong to a learnable class after some Booleanization. And then the other important thing is that these quantifications have to be independent. So if you have there exists y here for some combination here, and you say or something else, then the quantifications have to be independent inside this rule. Okay. Anyway, what I wanted to talk about today is a simple version of it, where I want rules which are just disjunctions of existentially quantified conjunctive schemas. So it's something like this, that maybe Z revenges X if, under the previous situation, that Z likes someone who was insulted, who was done bad to by X, or there's some other conditions under which Z may want to revenge X. Okay, so the idea is that in many natural cases, it's a bit like disjunctive normal form. There are a finite number of different cases which exemplify a certain number of typical situations. Okay, so this is, in fact, all the examples I had for doing robust logic fall within this core robust logic class. And then the observation is that if this is what you want to learn, then, okay, sure, then you can make LLMs learn these too. And we won't change the LLM software and hardware too much. And then to be able to learn these rules will amount to some class which is provably learnable in the sense understood in this room. And so I'll explain what that means. But maybe a very simple thing to explain is that it's believed that when a large language model makes a prediction of the next syllable, it's believed that, of course, internally, it's analyzed all these relationships and all this complicated stuff about the world, okay? And it does, under the hood, it must be doing something similar to what I'm hoping for. But once it's predicted the next syllable, all that information is lost. And then for the next token, it has to recompute everything, okay? So basically here, the proposal is to be slightly more sensible. And okay, so this is the proposal. So I want to break up the training and the testing stage of LLMs into two stages where I help the system to do relations. And so the idea is that instead of your current LLM has these tokens, so now I'll expand the token into, say, maybe 4 tokens. And this will be something like the token in the LLM. So it'll localize all the properties of this object. Okay. So the main problem with LLMs is that when it refers to Joe here, Joe there, Joe there, it somehow has to be a genius to figure out somewhere in the network that's the same Joe. Okay. These relationships, figuring out the relationships is this mind-boggling thing which it spends hundreds of millions of dollars being trained for. Okay. And so surely we understand this and we should try to help it. And because the fact that there's one Joe and there's one someone else and they have properties, and surely if you bring together the properties locally somehow, you make the task easier. So that's essentially what we try to do. So we'll expand the token set by some small factor, maybe 4, and then there'll be this little world of other properties Joe has, which will be brought to it. And then, so we have inputs, and they'll be encoded into tokens as currently, but in a more expanded, called Integracode. This kind of things are made more explicit in a more expanded code. And then this will be used both for training and in testing. Okay, so what is this code? Okay, so the idea is that, okay, so when I analyze the sentence, Bob insults Joe, et cetera, then Joe, instead of staying as a single token, somehow locally to Joe, or to where Joe is mentioned, I'll bring the further relations that Joe is the object of being insulted and Joe is the object of being liked. Okay, so these verbs have subject and objects, whereas Bob is one insulting and is the one who will be revenged. Okay, okay. So I put more information locally into these tokens. Okay, so the word token is used in 2 very similar senses here, but they may as well merge. Okay, so then. So this is on training, and in inference, what you want is that. Okay, so in inference, what you want is that when you do the inference, initially the sentence you're trying to infer about will be parsed in the normal way. But then you may want the system to be able to do to predict that revenge is going to happen. Okay. So it's going to learn rules, and and it'll be able to chain together these rules and, in that sense, do reasoning. Okay. So here again, same thing. Instead of a single token, I expand it out into H tokens, and these are these Boolean tokens. Well, in real LLMs, of course, a token kind of isn't one thing, but it's some big vector of things. And in this Boolean version, this Joe vector will be lots of zeros and a 1 just in the Joe entry, and then that's usually mapped into an real vector embedding, which is more compact, and we can do exactly the same there. Okay. So the so what I'm doing isn't any great mystery. So if you've got a rule like this, which you're learning, then you can look at the arity of the relations, and what you want to care about is the maximum arity of one of these conjunctions, which in this case is 4. Okay, so if you've got a disjunction of these conjunctions on the left-hand side of the rule you're trying to learn, then the critical parameter is this maximum arity on the left-hand side. And then it turns out that in this representation, for each robust logic rule like this one, of arity for k, that is corresponding k-DNF Boolean formula in terms of this representation, which is pretty good. It's a heuristic in that it's accurate on scenes where each relation is used just once. So what's going on here is that the full relational world is expensive to implement in a if you've got these huge windows in LLMs, that may be expensive to implement. So we do a shortcut. So we bring together in the same place the relations which act on a person, but in some sense we break the two ends of the relation. We still don't tie it together rigorously. It's the language which ties it together. So if I say, I like you, and there's an object of like and a subject of likes, then the fact of the language will tie them together. So text in which there are 20 people all revenging each other will probably be not the right text to learn from. The notion of, so you learn from simple cases. So this is something which where there's a provable theorem which is relevant to simple cases of the phenomenon, which one can implement quite efficiently. Okay. Okay. So this is. Okay. So I'm just repeating myself. So okay. Okay. So the summary of this is that these core robust logic rules are learnable in a defined sense. I think very important is that this code, we expand the code, so language is a bit too implicit. Okay, we may like natural language, it's a bit too implicit. So we help the system to make explicit some of the relationships. And one good thing about it is that when we call the thing many times, so currently large language models use natural language as the kind of receptacle of the different stages of its memory. Okay, so here we produce more explicit information about the relations, because this is where we believe the difficulty is. So we are trying to mimic this robust logic where there are theorems which prove soundness, and I don't know any other basis on which one can claim soundness for any kind of reasoning which is any close to what LLMs are trying to do. But I think that's a question of our day. Can we assign any rigorous notions, any notion of reasoning, any defined notion of reasoning to what LLMs are doing? Okay, that's the basic question. And now this is one attempt at tying the loose ends together there. Okay. So this is a method. This method is a heuristic, as I said. But it's a heuristic for a well-defined goal. So in the paper, I make this distinction that there are heuristics. There are heuristics for well-defined goals. You can have a heuristic for the traveling salesman problem, but just saying you've got a heuristic for I don't know what, that's a bit more dangerous. Okay, so at least you should declare what is a heuristic for. Okay, standard LLMs can be adapted to this. So just one concluding comment, which I think may be something in it. So of course, energy consumption is almost everything in this game. So whether by making this step we're on the surface we're increasing energy consumption, but in the long run actually we may decrease it, because if the difficulty of training at the moment is because the machine is trying to do too complicated things that are too complicated for it as far as establishing all the relationships, and if we help it, if we help it in this main difficulty by splitting it up into two stages, maybe the stages can be made simpler. So I think here there can be a big space of possible experimentation where one tries to reduce energy. Okay, thank you. Okay, you got this.
It struck me that I wonder if robust logic could be helpful in maybe like debugging LLMs or understanding like what is it that they have learned. So I mean, in some sense, the LLM has a lot of stuff in it, and you want to figure out like what's in its head. And so, so these sort of things maybe could be human understandable or understandable to another system, and maybe you look at it and say, it seems like this LLM has been watching too many soap operas, or I don't know, or whatever it is. But with the kind of rules it's built in, you might say, these aren't rules we wanted to have built in. There's something from what it's learned. What if you have sort of thoughts on that?
Yeah, well, great. Yeah, I mean, I think the a very natural question is, what are current LLMs doing at all? So maybe they're trying to mimic exactly robust logic, maybe not. But so if anyone could try to, establish in any way what LLMs are doing in relation to any formal logical reasoning system, that would be fantastic. Yeah, I think that's very important, because it's possible that it's exactly what LLMs are doing. I don't think so, but I think if we knew what it was doing and had confidence in it, then that would change our trust, I think, at least for people in this room. Yes, so yeah, you phrased it very well. Yeah. Yeah. Okay. Yeah.
Your example of robust logic was very simple, of course, for your presentation there, but would you include things like Aristotelian syllogisms as robust? Or we often use a more infinitistic thing with induction applied to certain relationships. Can we include those kind of things in a robust logic?
So maybe the term robust logic is maybe badly named. Okay, so maybe it's not that logical, but yes. So the idea is that I think any rules of inference you can express, I think you can program up. You can learn or program as robust logic, I think. But the robust logic doesn't make a choice among these. But any of these logics, I believe you could make the system learn, and then all it would supply for you is chaining. But in the background, there's also the idea is that it can support this chaining in situations which are uncertain, where all the rules are learned. Okay, so I think you're interested in programming some system where you know exactly what the rules of inference are. I think you can do that, but in addition, this thing is really geared for the situation where the rules are uncertain and you learn them, and with high probability, maybe they work in your world, maybe not in someone else's world. And maybe in human development, this is how it started. I think we started with this robust logic thing, and then when we started doing mathematics, we also dreamt up these logical systems you're talking about. So, okay.
finish up with one last question,
Okay.
which is, so is there an intuitive reason or an argument why an LLM, or specifically a very good next word predictor, cannot reason? Let's say cannot learn to reason?
Well, you tell me your notion of reasoning.
Logic, robust logic.
There's no reason for that. I think the way you could ask it is you could try to formulate how you test this, yeah. You could try to formulate the question of how, given a large language model, how you test whether it's doing this. So it's not quite clear what the test would be, because in some sense the representation in the large language model is not well defined. Okay, so it's hard to define. But again, I think it's a bit like Avram's question. I think it's very fundamental. It's what needs to be done. Yes.
We have a 20-minute break before the next session. Let's thank Leslie. We'll start at 11:15.
Just one remark. Well, you know, jag är ju